Good morning, students. Today I am going to explain about the difference between the order and molecularity of a reaction. Okay, if you will be asking a 2 mark or 3 mark question answer, please make a note. First, see the order of reaction. Order of reaction. It is the sum of the powers of the concentration terms involved in the experimentally determined rate law. Okay, the order is nothing but the powers of the concentration terms. Okay, that is nothing but order. The overall order is nothing but we have to sum of the powers of the concentration. Okay, and for molecularity, it is the total number of the reactant species. It is the total number of reactant species that involved in an elementary step. Okay, that is nothing but how many of number of reactant involved in a chemical reaction. That is nothing but the molecularity of reaction. Okay, and for order of reaction, it can be zero or fractional or integral. Okay, but in case of molecularity, it always a whole number and cannot be a zero or a fractional or integral. Okay, and at that point, it is assigned for the overall reaction. If you want to find the overall order for the reaction, means you want to add the order of the each reactant which is given in the power. Okay, and it is assigned for each elementary step of mechanism. Okay, each step is determining the step in a molecularity of a reaction. So, the example was given here. You can suggest the example to know the order of reaction by using the reaction which is given in the equation, which is given in the question paper. Okay, you can go through it. You can write in your rough note. If you have a note, please make a note and ask any doubts in classes. Okay. Let's move on to the next topic, integrated rate equation. Okay, we have just learned that the rate of change of concentration, rate is nothing but speed. Okay, the rate of change of concentration of reactant is directly proportional to that of the concentration of the reactant. For general reaction, A gives a product. Okay, this is considered as this is a reaction. A gives a product. Okay, and the rate law for this reaction is nothing but rate equal to minus dA by dt equal to K into concentration of A to the power x. Here minus indicates the decrease in the concentration, because decreasing in the concentration increase the product. Okay, by decreasing the concentration of reactant, it will be converted as a product. Okay, so in that places concentration will be decreases. For that you have to put negative sign here. Minus dA by dt equal to K. K is nothing but rate constant to the concentration of A to the power x. Power x is nothing but the order of a reaction. Okay, if 1 it comes means, if x equal to 1 means, it is called as a first order reaction. If x equal to 0 means it is called as a zero order reaction. If x equal to 2 means it is called as a second order reaction. Okay, if x equal to 3 means it is called as a third order reaction. If it is a first order or second order or third order, only you can clarify. When the power is nothing but 1, it means a first order reaction. When the power is 0, it is considered as a zero order reaction. Okay, please make sure on that. Where K is the rate constant and X is the order of reaction. Okay, the above equation is a differential equation. The minus dA by dt combined, it is called as a differential equation. Okay, so it gives the rate at any instant. However, using the above expression, we cannot answer a question such as how long will it take for a specific concentration of A to be used up in the reaction. Okay, what will be the concentration of reactant after a time t? What happened to the concentration of the reactant after some time? That is nothing but time t. Okay, to answer such a question, we need the integrated form of the above rate law, which contain time as a variable. Okay, to know what happened to the concentration of the reactant after some time, we need the integrated form of the rate law. Okay, which contain time as a variable. Let's see. A variable means t naught is nothing but initial time, and for t1 or t2 or t3 nothing but the final time. Okay, Integrated rate law for the first order reaction. It is very important 5-mark question. If you ask in a 5-mark question, please make a note. Very important. Okay. Integrated law for first order reaction. Okay. Reaction whose rate depends on the reactant concentration raised to the first power is called as a first order reaction. Okay. Let us consider the following first order reaction. This is considered as a first order reaction. Reactant A gives a product. Rate law for this reaction is nothing but rate equal to K to the power K concentration of A to the power 1. 1 indicates the first order reaction, okay, because it is called as a first order reaction, where K is a first order rate constant. For differentiating, we will get the answer of minus dA by dt equal to K to the concentration of A to the power 1, okay, to the power 1, okay. If you bring this concentration of A to the power 1 to the left hand side of A equal to, and we have to bring this T to this side, we will get the value minus dA by A equal to K dt. Integrate the above equation between the limits, okay, integrated the above equation between limits T equal to 0 and time equal to T, while the concentration varies from the initial concentration A0 to A. Here is nothing but A0 is nothing but initial concentration before the reaction start, and concentration of A, it is nothing but the final concentration after the completion of reaction. Okay, on integrated we get integrated of concentration of A not to the concentration of A, okay, minus dA by concentration of A equal to K integrated 0 to T dt. Okay, and after integration, minus ln concentration of A to the A0 and the concentration of A equal to K T 0 to T. Okay. After the separation this, we will get minus ln A minus ln concentration of A0 equal to K T minus 0. Okay, we will get like this. Okay, here minus into minus is nothing but plus, so we will get here minus into minus is nothing but plus, so we will get minus ln A concentration of A plus ln concentration of A0 equal to T minus 0 is nothing but T to T. Okay, here minus ln plus minus ln concentration A plus ln to the concentration of A0 equal to KT is nothing but the ln A0 by A. Ln A0 by A. This is the formula. Minus log A plus log B is nothing but log B by A. Like that, you have to put this equation. This is the formula is followed by formula. The formula is nothing but minus log B plus log A is nothing but log A by B. Like this, you have to follow this formula so that you will get ln A0 by A equal to KT. Okay, this equation is a natural logarithm. To convert it into usual logarithm with a base 10, we have to multiply the term by 2.303. Here we have to apply the value of ln. The value of ln is nothing but ln equal to 2.303 log. Okay, 2.303 log is nothing but the value of ln. So we have to submit that log here. 2.303 log concentration of A0 by A, concentration of A equal to KT. Like this, you will get after the applying the value of ln 2.303 into log. Okay, let's see here like this. Okay, and that if you want to bring the, you should bring the bring this T to the left hand side of equal to, so you will get the answer of K equal to 2.303 divided by T log concentration of A naught by concentration of A. Okay, equation 2 can be written as, this is nothing but an integrated rate law for the first order reaction. Okay, if the question is asked in a problem, the question is asked as a first order reaction means you have to use this formula. This is the formula for first order reaction. Okay, this is the formula for first order reaction. K equal to 2.303 by T log concentration of A naught by E. Okay, equation 2 can be written as to form a in the form of y equal to mx plus c. Equation 2 can be written as like this. Okay, ln A naught minus ln A equal to kt. Okay, if you bring minus ln A to the left hand side of equal to that, you will get, okay, if you bring, so we'll get a ln concentration of A equal to ln A naught minus kt. Okay, that is in the form of y equal to c plus mx. Okay, c is nothing but concentration of A and mx is nothing but kt. Okay. If you follow the reaction by measuring the concentration of the reactant at a regular time interval t, a plot of ln A against t yields a straight line with a negative slope. From this, the rate constant is calculated. Okay, example for first order reaction. This is called as a example for first order reaction. It will be asking me 1 mark, 2 mark question answers. Write the example of first order reaction. This is called as a first order reaction. Okay, nitrogen pentoxide react to give the nitrogen dioxide and oxygen. Okay, decomposition of nitrogen pentoxide and decomposition of thionyl chloride SO2Cl2. It is also called as a example of a first order reaction. And decomposition of hydrogen peroxide and isomerism of cyclopropane to propane. These 4 reactions are called as a example for first order reaction. Okay, next we see the pseudo first order reaction. Pseudo first order reaction. Okay, pseudo first order reaction. Let's see. It will be asking a 2 mark question answer. Please follow. The kinetic study of higher order reaction, it is difficult to follow. For example, in a study of second order reaction involving a 2 different reactant, okay, the simultaneous measurement of the change in the concentration of both the reactant is very difficult. To overcome such difficult, a second order reaction, okay, you have to write the answer for second order reaction from this. A second order reaction can be altered to the first order reaction by taking one off of the reactant in a large excess. Okay, in a reaction, if there is a 2 reactant means, if you want to take, you should take the one reactant in a large quantity, then only it can be altered as a first order reaction. Okay, such reaction is called as a pseudo first order reaction. Okay, pseudo first order reaction. This is an example for pseudo first order reaction. Okay, the hydrolysis of an ester, the ester compound ethyl acetate react with the water molecule to give acetic acid and methanol. Okay, the rate constant, the rate law for this reaction is nothing but rate equal to K, concentration of ethyl acetate, methyl acetate and concentration of water molecule. Okay, if the reaction is carried out with large excess of water, there is no significant change in the concentration of water during hydrolysis. That is, concentration of water remains almost a constant. Okay, now we can define KH2. Okay, if the reaction is carried out with the large excess of water, there is no significant change in the concentration of water during the hydrolysis. Okay, in this reaction, we should take the large excess amount of water to make the second order as a first order reaction. Okay, this is called as second order reaction. If you want to take the water molecule as a large content, it is considered a first order reaction. Okay, that is, concentration of water remains almost same after the hydrolysis of water. Okay, now we can define K, concentration of H2 equal to K dash. Therefore, the above rate equation becomes the rate equal to K dash concentration of a methyl acetate. Okay, then thus it follows a first order kinetics. Next, see the concept that is nothing but integrated rate law for the zero order reaction. Okay, this is nothing but a zero order reaction. Zero order reaction means the power should be a 0. First order means the power should be a 1, and the second order means the power should be a 2. Okay, a reaction in which the rate is independent of the concentration of the reactant over a large but a range of concentration is called as a zero order reaction. Such reaction are rare. Let us consider the following hypothetical zero order reaction. A gives product B. A gives product. Okay. A gives product. In this reaction, the concentration of product will be decreases. Okay, decreases. The concentration of reactant will be decreases as the time is increases. Okay, you can see by seeing this graph, the concentration will be decreases. The concentration will be decreases if the time is increases. Okay. Is increases if the time is increases. Okay, the concentration will be increases as the time is increases. Let's see. Okay. The rate law for the first order reaction for zero order reaction can be written as this is nothing but the A gives a product. Okay, for zero order reaction, the rate law is nothing but 8 equal to K concentration of A to the power 0. 0 indicates a zero order reaction. It is a differentiating equation, so we will get the minus dA by dt equal to K1. Anything power 0 is nothing but 1. Okay, anything power 0 is nothing but 1. Okay, anything power 0 is nothing but 1. So the concentration of A to the power 0 is nothing but 1. Okay, so here value. Here, if you bring this dt to the right hand side of equal to, so we will get the answer of minus dA equal to k dt. Okay, integrate the above equation. Integrate this equation between the limits of a naught at a 0 time t and a at a some time later time. Okay, so we will get minus integrated a naught to a dA equal to k 0 to t dt. Okay, by this, if we derive this, we will get the answer of minus concentration of A to the concentration of A naught to the concentration of A equal to K T0 to T. Okay, here A naught minus A equal to KT. If we bring this T to the left hand side of equal to, so we will get K equal to A naught minus A divided by T. It is nothing but the formula for zero order reaction. If some problems asking for find the zero order reaction means you have to use this formula. For first order reaction, K equal to 2.303 by T law of concentration of A naught by A. It is nothing but for first order reaction, and for zero order reaction is nothing but K equal to A naught minus A divided by T. Okay. In this case, A naught is nothing but initial concentration and A is nothing but final concentration. Okay. By using equation 2 can be written in the form of a straight line, that is nothing but y equal to mx plus v. It is enough to write from this only. Okay, no need to write this. You have to write the integrator of zero order reaction from this only. Okay, you can stop from this. Let's see example for zero order reaction. This is called as example for zero order reaction. It will be asking 2 mark or 3 mark question answer. What are the examples for zero order reaction? Photochemical reaction between hydrogen and iodine to give a hydrochloric acid. Okay, and decomposition of a dinitrogen oxide, nitrous oxide. Okay, on hot platinum surface, and iodination of acetone in acidic medium in a zero order with respect to iodine. These reactions are called as an example for zero order reaction. Okay. Okay. And next we see the half-life period of a reaction. Half-life period of a reaction. It is a very important 5 mark question, or it will sometime it will ask in a 2 mark or 3 mark question answer. Please make a note. Half-life period of a reaction. The half-life of a reaction is defined as the time required for the reactant concentration to reach one of its initial value. The simple method, the simple concept for half-life is nothing but time required to reduce the one of its concentration of a reactant. Okay. What time it will take to reduce the concentration to half its value. Okay, and that means the half-life of a reaction is defined as the time required. Okay, the time is needed to reduce the concentration of a reactant to its half. Okay, to reach concentration to reach one of its initial value. Okay, from its initial value. For first order reaction, the half-life is a constant, that is, it does not depend on the initial concentration. For first order reaction, the rate constant for a first order reaction is given by regarding half-life period. Okay, for first order reaction, K equal to 2.303 by T log A naught by E. Here T is nothing but T of, because of half-life period, the value of T is nothing but T of half-life period. Okay, and A, the value of A is nothing but A naught by 2. Okay, A is nothing but initial concentration. A is nothing but initial concentration. We have to find the half-life of the half of the concentration. So A naught by 2. A naught by 2 is nothing but A naught is nothing but the initial concentration. A is nothing but final concentration. Okay, A is nothing but final concentration. So we have to divide by it. We have to take the half of its initial value, so that we will put by 2, A naught by 2. A naught is nothing but initial concentration before the reaction proceeds. Okay, that is nothing but A naught. So we have to put these values to the equation 1. So we will get the answer of K equal to 2.303. The value of T is nothing but T of equal to A naught divided by the value of A is nothing but A naught by 2. A naught by 2. Okay, here after the reciprocal we will get A naught into 2 divided by A naught. After the cancellation of A naught, we will get answer only 2. So log 2, we will put log 2. K equal to 2.303 by T of log 2. Here the value of log 2 is nothing but 0.3010. Okay, the value of log 2 is nothing but 0.3010. In that we have to apply the value of log to the equation 2. So we will get, after the applying the value of log 2, we will get 0.303010. Okay, this is nothing but the log 2 value. After the applying the log 2 value, we will get the 2.303 into 0.303 divided by T of equal to T of. Okay, after the multiplication, we will get the 0.6932 divided by T of. Okay, if you bring the T of to the left hand side of equal to and K to the right hand side of equal to, so we will get the T of equal to 0.693 divided by K is nothing but the half-life period for first order reaction. Okay, and let's calculate the half-life period for a zero order reaction. Okay, the formula for zero order reaction is nothing but K equal to concentration of A naught minus concentration of A divided by T. Okay, the value of T is nothing but T of, and the value of A is nothing but A naught by 2. Okay, after the applying, we will get A naught by 2 into T of. After the reciprocal, here after the reciprocal, we will get A naught divided by 2, okay, into 1 by T of. So we will get A naught divided by 2 into T of. After that, if you bring this T of to the left hand side of equal to, and we bring the K to the right hand side of this equal to, so we will get a T of equal to A naught by 2 K. So T of equal to A naught by 2 K is nothing but the half-life period for zero order reaction. Okay. Hence, In contrast to the half-life first order reaction, the half-life of zero order reaction is directly proportional to the initial concentration of the reactant. Okay, and some example is given there. You can try it our example in your note. Okay, if a note occurs, please make a note and ask. Okay, before that you have to see this video again and again to clear understanding. Remaining we will see in the next class. Okay, thank you.